Okay, chapter 7 is application of principle of energy. Okay, again, just recap. Your test 1 already done. Test 2 will be focused on rigid body. So chapter 7, we will look at work and energy. So again, recall what is work. Work, you deal with two things only. Two vector. What is work? Work is when force do what? Do work. How force do work? When force move what? Go parallel with the distance or displacement. Okay. So then energy. There are only two types of energy, kinetic and potential. So kinetic, half mv squared. In rigid body, you deal with angular velocity, angular acceleration. So half mv squared, the v actually is your velocity. So and you always use the tangent velocity, right? So no matter it's move, let's say you move in a straight flat surface, then you use the normal velocity. There's no rotation, there's no nothing. So you just use the normal v. But if the rigid body twist or turn or rotate, then there's an angular. You still need to use the v, right? But you link the v with the angular parameter, v equal to omega r. Okay, so that is how you find kinetic velocity, kinetic energy, half mv squared. Still use back the half mv squared. Then potential is what? mgh. But you have to, now in chapter 7, you should give yourself datum already. Datum will not be given. You should already give yourself, okay, I refer to this point, this level. So this level is my datum. So above datum, positive potential, below datum, negative potential. Then what else? Okay. Yeah. Basically, is you just call back what you learned in previously. Now you deal with rigid body. Just need to be careful if there is a moment. For example, m equal to I alpha. Then there's one equation that moment will create acceleration also. Moment will create energy. Okay, sorry, not energy, work. Okay, now force. When you force parallel with the distance, it create work, right? Now you imagine one rotation body, moment, right? Moment, how moment do works? What is the parallel distance? Angle, right? So moment times the angle, you get work. Makes sense, right? So force, you times this time or time the displacement that parallel to it, you get work. But when you're given a moment also do work when you rotate at a certain angle. Because this angle was parallel to the motion of the moment. So moment times the change of angle, you get work. Okay, so that is the thing lah. So but anyway, I'll still go very slow. So kinetic energy, let's say you have this random body here. We have x and y, point P, x, and there's a rotation omega. So still same, what is the kinetic energy? Half mv squared. dm is very, very small portion, but you want to get the total means you integrate lah. Okay. So at the end, you're still calculating half mv squared. Right? And the v here, how you find v is referring to relative velocity. So in this case, if you have I and P, I stroke P, V, I stroke P, you can write VI minus VP. Then rearrange, you want to get positive equation. So Vi equal to Vp plus Vi/P. Get this equation, right? Then you put in, you know that this is vector. Vector you can split into x and y direction. So when you deal with vector, then you have I, J, K. Okay. Um, okay. What else, okay. V is omega R. So Vp, this one, Vp, you have x and y. So you have Vxi, Vpy, J for this one. So this one, this is here to here. Right? Point I from P. So is this resultant R here? So the resultant R is a velocity. Velocity equal to omega R. Omega, this one rotate anti-clockwise, right hand rules, positive, negative. Positive. Huh? Okay, so that's why positive K. Omega R. What is your R? This is your R. Split R, X and Y. So R equal to Xi plus Y. So go home, practice how to do cross products. All right. So I will not go deep into derivation. You go home and read. Okay. Quite lengthy, yeah. I will not test you how to derive this one. At the end, just show you lah. I have do all this work for you. So at the end, rigid body, rigid body kinetic energy. You have a few components. First one, when you do particles or the previous physics class, half mv square, you are focusing on the mass effect. Second one, if you're rigid body, then you have a center of gravity effect. Third one, you have initial effect. The two components here, you don't learn in your normal physics class because you simplify everything. But when you come to dynamic class, you consider mass, you consider center of mass at G, you consider moment of inertia. So you will see three components. So the first component, half mv squared, you're very familiar. Second one, moment, the center of mass of the energy. You can see here is integrate of your y dm. Okay, center of mass. You still remember how to find x bar, y bar, right? This is your y bar. This is your x bar, right? You use the mass divided the xm divided by the mass. Okay, that one. Okay, so your equation when you deal with rigid body kinetic energy, you have mass effect, center of mass effect. So you'll see ym and half omega square I. This is the second moment of inertia. So here, what you need to memorize here is that for moment of inertia, there's one equation new for you. Energy, you will create energy, omega square I. This energy equation for rigid body. Then this one, you also need to try to understand like what is the format for center of mass that create energy. Okay. All right. So in special case is point P correlate with G. Means this any point that the P was exactly at the center of mass. When the center of mass, then this one you can take out already. Because when you find your x bar, y bar that you learn in your statics, it was same place as the center of mass, center of gravity. Center of gravity or center of mass. Center of mass will give you this one. So here the effect of central of gravity you can cancel because y prime s prime is 0. So you cancel, then only leave out the moment inertia and the mass effect. Okay. Okay. To yeah. So this is how kinetic energy works. If you look at the rigid body again, initially you have 3 components. So at least you should understand the background theory a bit. Rigid body, you have when you calculate kinetic energy, you have 3 effects. First, you look at the mass, which is normally you calculate for your physics class, half mv square. Second one is the center of gravity. Then the third one is moment of inertia. So when your center of gravity, G point, is the same the interest point is the same as your center of mass, then you can cancel the middle one. Okay, means balance system. If imbalance, then you need to calculate the middle one. Okay, then inertia cannot go, cannot run away. So today you learn second session, you learn one more new equation, which is half omega squared I to calculate energy, kinetic energy. Okay. Okay. So again, this equation is when your central your interest point is at the center of mass. Then only you use this one. If the question give you like unbalanced this, then you cannot use this one. You have to add one more component, which is you need to find y bar, x bar. Okay. So you look at this equation. If you have object that do translation, what happened to this equation? You have this object moving straight line. What happened to this equation? You understand translation motion, right? What happened to your omega? What happened to this term, omega? Huh? What is omega? Huh? What is the name for omega? Omega, what is that? What is omega? For example, A is acceleration. Angular velocity. What mean by angular velocity to you? Okay, what happened to the body if you have omega? It rotates, right? So if you have body that move in the straight line, what happened to the omega? 0. So you can cancel this one out if the object move in straight line. That's why in your statics, in your physics, you don't consider the object rotating. Now you see it now. So in your physics, in your SPM, in your static class, you don't see the object rotate. You only see the object move in the angle, move in the flat surface, or fall from the straight line. It never say the thing rotate until you learn dynamics. And then you rotate angular things. Okay, now I hope you see the difference here. Okay, so you only left out this one. Yeah. So you need to read carefully the question. What kind of motion you have? Right? So If the object move straight line, then it rotate, then you have two equation already. First phrase, second phrase. Because you know energy cannot be destroyed, but it can transform energy. That one you need to keep in mind when you deal with energy. Okay, rotate, then you have the both lah. Okay, make sense? And here we are focusing on center of mass. Yeah. Okay, the rest I think you can read, but I just highlight the important one. Can okay. Then only you go to the V equal to omega R. Just now you move too fast already. All right, don't straight away jump into this. You try to observe what is the motion, how the object work first. Then you try to think, how do I analyze? Okay. Now again, you look at the equation that kinetic equation. What actually you can find from this equation? Velocity. Kinetic energy solution always give you acceleration, either in angular or normal acceleration, normal velocity. Make sense, So if you see the question asks you to find velocity or angular velocity, you want shortcut, you use energy equation or use conservation energy. Later, we will talk about conservation. So it just give you hints that you look at the question, you agak can know what equation you want to use already. Okay. So you further develop V equal to omega R. You change all the equation into angular terms. If the object rotate, okay, because you don't want to confuse yourself with the normal velocity and the angular velocity. If the object rotate already, you change the whole equation into angular terms. Okay, once you have angular terms, you have this half mr square plus ig omega square. Do you feel familiar with this one? Ig plus what? Md square. What is this? IO. Okay. So this equation is when you refer from a certain point, from this point, then you get this. Okay. Okay. The rest you read. This is we are using parallel axis theorem. The term inside parenthesis represent the moment inertia IO body about axis perpendicular the plane of moment pass through O. It just means that this is like a paper. This one rotate on the paper and the axis is going up. Okay. General plane motion, you know general plane is combined of two, translation and rotation. Right? So don't confuse yourself. You're still using the same equation. T equal to mass effect and second inertial effect. Half mv square plus half omega square I. So in this case, again, we assume that the interest point was same with the center of mass. If it's not same, then you have to calculate the central one. Okay. So you can combine. You can also use kinetics. This whole equation. You can also use IC equation. You can combine these two into IC terms. Right. What else? Work. Okay, work. Again, work you already familiar already. When force do work, when force go parallel with the distance traveled, it create works. Right. Now, although this diagram look a bit complex to you, Just you know that when object move in the circular motion, just call out this small section in radian. When the force go through, always perpendicular to this curve here, right? For example, you have a force pushing the disc along the thing. The force actually go through the same distance here. Makes sense? So how do you find the distance S here? S equal to R theta. So what is work? U equal to Fs. So force you multiply by R theta. Okay, so you need to recall this one. So just think how the force work. So this basically I explained on the whiteboard here. So you already know like okay, all this you can read lah. So same concept. Okay. Constant force again. What I need to highlight here is always have your force and distance of surface put parallel. When you have force, you have surface, contact surface, always put your focus on the surface, contact surface. And then convert all the force parallel to the surface. Don't chase after the one that you can manipulate. Yeah, don't like, okay, I want to turn my surface along the follow my force. Then can also you still get the same answer, but you are actually confusing yourself. I find it more confusing lah, but maybe for you not confusing, right? Both get the same answer, right? But I would recommend you focus on the surface. Okay. Weight also do work. With is your for example this one. So if your datum is here and the object is above, so you're doing if displacement is upward, work is negative. We now deal with work, not energy. Don't confuse mgh with work. This is work. Work, you focus on the force and the distance traveled. So here, weight of the body does work only when the body's center of mass undergo vertical displacement y. So if the displacement is upward, work is negative, since weight is opposed displacement. So if go down, then you get positive work, because work and distance same direction. If work, you know that not work, your weight W, your W always pointing down. But if you're throwing up, your displacement actually pointing up, right? So you're throwing up, but the weight is still pointing down. So when you have two vector that opposite direction, you get negative. Make sense, so this is the careless mistakes that always appeared in the assessment. Hey, so this is negative because it's moving upward. Okay. Spring. You have spring system in your final exam. Just for your info. So spring force, again, spring force, we now deal with work. How spring create force? How you calculate spring force? K multiplied by distance traveled by the spring, right? Then work, you take the force multiplied by the distance traveled, right? So you actually have the this one. Work is half KS squared, right? Right. So you have negative work before minus work after minus work before. Fixed already, huh? So the derivation of this one, you can go back to the, I think, chapter 4 or chapter 5. Yeah, okay, yeah. So you go back, there's an equation to derive this one for the spring. Huh? But now we don't need to derive the equation anymore. So for the work, you have half k square, and then you take the behind. But this one is negative. Huh? Okay. It's negative because displacement of the body is opposite direction of the force. Okay. Okay. They are work. They are forces that doesn't do work. I need to highlight this one. Huh? When your force is at a fixed point of the body, or they have a direction perpendicular to the displacement, means work is you must always parallel. But you have perpendicular, then no work. So what are the forces that do not do work? For example, the one you see here. What doesn't do work? This one do not do work. Because it's always pointing perpendicular to the distance it travels. And what else? Normal force also. But friction, it depends. Okay, it depends. I need to highlight this one. Memorize this one. Because most of the time you will forget this one when you solve problems. Friction force acting on a round body as it rolls without slipping over a rough surface does not do work. Yeah. Friction force acting on a round body. It means you have wheel shape, roller shape, anything that is round acting on a surface do not do work. Why? Friction acting on where? One point. But it's flat surface, then if you have a box on the flat surface, then do work. If you have a flat surface, the contact surface, then this one friction force do work. Huh? This one got do work. Huh? But you have one circle wheel, bicycle wheel or butt wheel. Only one contact surface. Only one point. Then this friction force do not do work. Okay. Although your free body diagram, you need to put in friction force. Yeah. The word is without slipping. You'll see this one in the coming assessment. You just highlight again and again. Don't calculate friction force for your work. Yeah. How tires work? How tires contact with the surface? Is it contact like this or contact like this? So again, look at the slides right here. Forces at either fixed point. There's a fixed point. Okay. 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 This is work. It do not mean it do not have friction. At the wheel. It do not means it do not have friction force when the wheel touch the ground. They still have friction, but that friction do not do work. Okay, I need to highlight that one. Don't say, hey, sir, I don't need to calculate, then wrong. You still need to calculate the friction force. Yeah. Okay, now when you have moment, You can break your moment into forces. How? By break your moment into couple forces. How? You change this one into couple forces. This one, you modify it become two forces from the center of the object. How to get M? This is R, right? The R is here to here. Because if you close this one, you get total moment, right? F multiplied by R, you get moment, right? Or you can put in the center. This is half R. You are seeing two moment. Moment, first moment, half R multiplied by F. You get half moment plus another half moment. Be careful on the direction of your force. This one clockwise, so your force must also show you're rotating clockwise. Don't change. It must be in sync. It must sync up with the moment. Make sense? Okay. 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 So this one is just a derivation on the coupled moment just now. So okay. So it just tell you that how to calculate the moment, half moment. So for example, here you calculate force and distance, right? This distance here. So how you calculate S here? R theta. This is your R, the theta. So you get your S, right? But the concept still same. So the work done by the moment, if you derive the equation, Fr is what? Moment. Moment multiplied by the theta actually is a change of angle. So it give you, I need to highlight this one. Work is positive when moment and the theta have the same sense, means same direction. The moment and the change of angle is positive, is the same direction, then it will give you positive work. So you continue to do integration, you will arrive at this equation. So moment with a change of angle, especially rotating angle, especially for rigid body that you rotate, then it's a change of angle, you see moment, then there's a work done. This is something new for chapter 7. You need to remind yourself, moment multiplied by change of angle, but must same direction, right? Then you only get positive work. Okay. Okay, we do one example, then we call it a day, right? All right, now example 1. You start to see spring already. Spring, rod, P, moment. Everything come out already. Pin. So bar shown in the figure have mass 10 kilogram. This one, 10 kilogram. Subject to a coupled moment M. Force P, which always apply perpendicular to the end of the bar. P always perpendicular to the bar. Also, spring have unstretched length of 0.5. Means before you stretch it, you have 0.5. A bit misleading diagram. Why? Because this spring will attach to B, and the distance from this pin to this slot here is 0.75. Don't treat by the diagram. So means before it mount, it's a bit shorter than this one. So okay, then you continue to read. Remain in vertical position due to roller guide in B. Means no matter how you turn the thing, this spring will always vertical. No matter how you twist it, the rod twist, it was still vertical and it was sliding. Determine the total work done by all the force acting on the bar when it has rotated downwards from 0 degree to 90 degree. So you have two cases. One, before stretch theta 0. Theta 0 is where? Go up. And it gives you rotation like this way because of the force here. And it gives you angle. Angle is 0 to 90 degree, means very straight. Okay. Now, before you move forward, read carefully the question. What question want you to focus on? The rod. Total work done by force on the bar. Means you focus on the bar. Okay. Now, when you focus on the bar, although this is rigid body, don't forget, you always need to put in the center of mass, G, in your free body diagram. Because as you learn more and more, you tend to forget already. Actually, there's a center of mass there. So remember, rigid body always start with the center of mass. Go and pinpoint where is the center of mass. Then draw W, go down in your free body diagram before you forget. Because you see, this example one, you have too many things to consider already. Then you forget. You tends to distract you from considering the weight. You read it, then you can do the P, spring force, moment. But you were like you want to solve, but you forget the fundamental. Actually, there's a weight there. So remind yourself. Don't forget about the fundamentals. Okay. So you have all these things. And then when you have this kind of problems, try to draw before and after. You try to like dissect the motion before and after. What's have changes? What have changes before and after? Because the diagram will be misleading, especially it's not scalable. I mean, it's not one-to-one scale. So you might be look all right, but when you draw it, then your calculation might wrong, especially the spring. Okay, you draw free body diagram. So there's a pin, positive, negative, right? There's a y and x axis. Okay. AY, AX. Then there's a spring at a certain distance at 2 meters. Then P always perpendicular. Then this is the one that always forget, your W at center of gravity. What else is missing in the free body diagram? Moment. We need to put in moment. Okay, I think we have all. Just need to put in angle. What is the purpose of putting angle? Because later you need to use work for moment. Okay, so you have a free body diagram and then the length and so on. Okay, understand? Okay. So this is a question diagram. This is a free body diagram. So you need to change from 0 to 90 degree. So the weight W. So what's the W displacement? How many W displace? From 0 to 90. How many it displays? How far W move in this diagram? Huh? Huh? Okay. This is your rod. let's say my W is my weight is here, center, right? My rod is from 0 to 90 degree. This is 0. This is 90. Does my G move or not? Huh? My G move, right? From here to here. How far my my W move? Huh? Yeah, 90 degrees angle. But how far your W moving? Thirty. Where is 30? 30 is what? You know what I'm asking now? You know what the question now? You know what I'm asking? I'm asking you the W, this one. How far this W move if you turn the bar 0 to 90 degree? How far your weight moving from initial location to the final location? How far your W move? Yes, answer is 1.5. You understand why 1.5? Explain. Explain to your friend why 1.5. You understand what I'm asking or not? You seem you don't understand what I'm asking. Zero degree. Ninety degree. How far your W have moved?
Same thing from the initial market. Same distance.
This is the initial location, right? Where is the initial location? How far your W move? This is original location. How far your W move? Huh? How far? Simple logic, huh? Okay. Why positive? Huh? No, what? How you get work positive? Yes. Still go back to the fundamental. How you get work? Force and displacement. Two are vector. How you get positive when two vector go parallel direction? So your W go down, S also go down. So positive, right? Try to think how we re-engineer this question in your final exam. If we release from 90 degree to 0 degree, what happened to your work? Try to think. Okay. Support moment M. How moment do work? How moment do work? Moment times what? Angle. So you change from what to what? 0, 90. Same direction or not? 0, 90. Moment, what direction? So positive. Here you use radian. Don't put 90. You put 90, gone. Okay, moments times the change of angle, both same direction, so you get positive. Okay, what else? Spring force. Spring force a bit tricky. Okay, when 0 degree, the spring actually being pressed, not pressed, being stretched already. The original spring, the length is what? 0.5. The gap here is 0.75. So at 0 degree, what is the length of the spring? 0.75. Can you imagine? So actually, before start, you're already stretching your spring 0.25 already. Makes sense. Then at 90 degree, here is 2, right? You change 90, 2 plus minus original length, 2.25. Your stretch final 2.25. This one you need to imagine a little bit. Yeah. Okay. Substitute inside the equation, half ks square, you get negative. What about point F? Point P. How far the P traveled? P. From 0 to 90 degree. How far does it travel? Huh? 3? No, not 3. 3 is what? 3 is the radius. Oh yeah, 3, correct. But you're calculating work, not moment. Moment, yes lah. P times 3 is moment. But we're not calculating moment. We're calculating work. So what is work again? The definition? No. What is work? What is the fundamental definition for work? If you have force, force must be parallel to the distance. So again, your force is perpendicular to the rod or waist. You try to imagine what is the motion if you stand at P. Does it move in the linear or it move in the circular? Okay. Circular from 0 to 90 degree, what you get? Is what I write, the same I wrote on the whiteboard there. So your P is here. Is at the end and always perpendicular. P times what? Distance traveled. But you must use radian. Okay, so F times the S here. How you find circumference? R theta. R theta, theta here is 90 degree. 90 degree in radian is what? Pi over 2. Okay. So I'm not going deep into calculation. So this is 90 degree times the S. You get 4 point something. You can put in term of pi if you want. Okay. Any question for P? Okay. What about pin reaction? Does pin do work? Why? Fixer. They do not do work. So you add all the force together. You get this one. Okay. So this is okay. So this is how you calculate work. Then later you link with the principle of work and energy. You find something like, for example, what is the angular speed of the angular velocity of the rod when you turn it. So that one later, but it link with what you learn. Okay, so we original before means you buy the spring, it give you 0.5. The original length without any pulling. You just put on the table, it will just give you the length. Here. So the unstretched length is 0.5. So before you mount on B, it gives you 0.5. So the distance between this slot and this pin, when it's 90 degree, right? When it's 90 degree, the length here is 0.75. So 0.75, but your spring original is 0.5. So you're going to stretch already. Can you see? So no matter how you want, also when you mount this spring at 0 degree, your length already reached 0.75. So you need to like stretch your spring to mount on this spring. So that's why before you already stretch 0.205. Okay. This example is stretch. What happened original is 8. Then it's compressed already. Compressed, then the equation will be negative. It means the x will be negative. But still you get positive value because it's square. If you calculate work, you still get the positive value. Okay, all right. So we stop here. See you next week. All right.